Okay, so happy Wednesday, everyone. Is everybody signing the attendance register?
I don't know what is it.
Yeah, it's good.
Ah, okay.
Good, it's being passed around somewhere? Okay, over there, good, good. So my name is Robert Laramie. I'm coming from the computer science department. And I'm very interested to see the register to find out where everybody here is coming from. Anybody here from computer science? That would be very surprising. Good. So if you want to find out more about me, I have a web page on the Swansea University website. And I've also set up a YouTube channel. It's called DataViz Bob, the YouTube channel. So if you're interested in seeing this material that we're going to just introduce today in more depth, you can visit that YouTube channel and then get more. Actually, you can get the whole course, all 20 lectures or something like that, because we teach a 20 lecture DataViz module over in the computer science department. So you can see them all there. This is also quite an exciting seminar because the way it's going to proceed is actually going to be influenced by you. So we're going to give a short introduction to the topic of data visualization, and then we're going to show some examples. But the examples we show are actually going to be chosen by you. Right? We won't be able to show all the examples because there are 9 of them and it would take a long time, it would take all day. But the ones we actually show, you're going to choose. So that's very unusual. Yeah, so if you decide to stay awake, you can choose which example. So it's really like, today it could be called data visualization by example. That's what the class could be called. But before I start with the actual material, I do have a little announcement. Maybe this is interesting for some of you, maybe it's not interesting, or maybe you have friends it's interesting for. We have a conference next year that we're hosting. It's called Computer Graphics and Visual Computing 2018. And it's going to run in September of 2018 at this university. Some of you might be interested in attending and some of you might not be, but just in case you know somebody that might be interested in attending, there will also be some state-of-the-art data visualization being presented at that conference, and it just happens to be right here, so it's really convenient. Some of you might need like training opportunities and stuff like that for your studies, and that's a great opportunity. Yeah. Happy Wednesday, Indigo. So this title slide said the age of data, right? It used to say the age of data chaos. And this diagram is a diagram about a ubiquitous pattern of knowledge evolution that we're collectively experiencing right now. Right, so this is, I'm going to describe something to all of you that you're already familiar with, but it's going to be worded in kind of a new way, in an organized way. So we all know, this is a pipeline, and it describes knowledge evolution. It's actually an abstraction of something happening inside your heads. So we all have real world challenges, right? We all have problems we want to solve. We all have understanding that we're trying to gain, and we all have knowledge that we're trying to advance. That's what you're here for, right? You're probably a PhD candidate, and you're trying to advance your knowledge. You're trying to reach a new understanding that you've never reached before, right? You have a goal, right? And that's where we all kind of start. It's something that we all obsess with and we're all very familiar with. Now, to achieve our real world goals or challenges, there's always a physical or analog approach. For example, if I said, please build a car, right? You could theoretically get out your blowtorch and your hammer and your other tools and raw materials and build a car. It is possible. It's not very easy, right? It might take you a long time. But you know it's possible, right? How do you know it's possible? Because we see so many cars everywhere, right? So we know it is possible to build a car, right? But if I asked you to build a car, why would that be a challenge? Exactly, you don't know how, you don't have the tools, you don't have the raw materials. So, do you see that the first three stages of this pipeline, this is a pipeline that represents a generic pattern of knowledge. So we just described the first three stages. We start with a challenge. We know there's a physical approach, but we also know that for a lot of physical or real world approaches, it's just not feasible. It's too expensive usually, or it's too costly in terms of time, right? So we run into sort of a wall or a barrier. And then, because we run into a wall or a barrier, I can't build a car, for example, we jump over to the digital world, so that this digital line, this dotted or dashed line, it's also a digital line actually, separates the real world from the digital world. That's what that, so in our thinking, we actually think, I can't build a car in the real world, but you could build a car in software, actually. Right? You can go to the Department of Engineering. Anybody here from engineering? So we can go to your department and say, I would like you to build a car in software. And that's what you do in the Department of Engineering. You can get out your simulation software, your CAD tools. You actually build the parts in software, virtual parts. Then you create your 3D mesh. Right? Then you run the flow simulation. So you can build a car in software. That's just one example though. Right? This is the general, this is the way we think for all of our problems. Right? Anytime we have a challenge or a goal we want to reach or a new understanding we want to reach, we always think, oh, there must be some software that can help us with that problem. Like, and if there isn't software that can solve that problem for us, we can build it. I'm sure I can pay somebody to build this app, right? There's an app for everything nowadays. So that, I haven't lost anybody yet, right? So everybody understands this. Now, that has consequences too. So this idea that everything has a digital solution has consequences, and it brings with it a new set of challenges. And that's what that next red box is, data chaos. So all these digital solutions, all these pieces of software that we use to solve our problems create a lot of data. Where is the attendance register? It's gone? Okay. Has everybody signed it?
No.
No?
Yes.
Still in the corner over there.
The anticipation is amazing. So all the software that we use to solve our problems creates massive amounts of data. And that is a problem, right, or a challenge, let's say, because the bigger our data sets are, the more complicated they are, the more difficult it is to then create knowledge and extract understanding from them. Has anybody tried to do that yet? Probably Indigo has. Has anybody actually tried to take a large data set and extract information and knowledge from it? Good. And so you know how difficult it can be. It's very difficult. So that's what we're here for today. So visualization, data visualization is the solution to this data chaos problem. It's one of the solutions. Right? Basically it's a science or a tool we can use to generate new information and knowledge and understanding from large, complicated data sets. That's the idea. And we're going to go over lots of examples of that today. Sound good? Everybody understand? So these are just some examples of this data chaos, and I think you can all relate to at least one or more of these. So if you're in engineering, you know that there's just endless amounts of CFD simulation data, right? If you're from physics, anybody here from physics, you know that there are endless data sets from imagery and experiments, right? Your supervisors have spent their whole careers collecting data. Any marine biology people or bioscience? Yeah, one bioscience?
No, medical stuff.
Okay, that's the life science.
Related, yeah.
Life science, yep. So we have an active bioscience department here, and they collect lots of data. Anybody from psychology or sociology, right? So you collect endless amounts of survey data and EEG data, maybe, depending on which side of the psychology world you come from. Sports science, anybody here from sports engineering? They collect endless data too. Well, everybody collects endless data, but anybody know what sports scientists collect? Anybody look into that before? They have endless videos to watch of games to try to figure out what's happening, to develop good strategies. Anybody from arts and you're gonna no, I'm using this as a temporary Okay, oh, we were going over the examples. Yes. So on the left side, those are sort of examples that come from careers or professions, right? Those correspond to people's careers, like what they do for a living. On the right side, those are a little bit more personal sources of massive data sets that affect you directly, like everybody directly on an individual and collective level, right? So whenever you make a bank transaction, the data is stored somewhere, right? Big Brother is watching you. Whenever you make a phone call, right, that's data is being stored somewhere. Whenever you buy something, right, there are cameras watching you. That transaction is logged, right, in a database. Whenever you visit a website, right, every keystroke you make is stored in a database. Right, every time you go somewhere, right, that data is stored, right? So it's an endless. I think you get the idea. It's endless, right? Every time you visit the doctor, right, that data is recorded somewhere. You also collect your own data, right? You collect photos and text messages, maybe, and emails, videos, and you have files. Right, you have a collection of selfies. Everybody has a collection of their favorite selfies. So this is really everywhere. Everyone is involved in this. So it's really the age, what I call the age of data chaos. And partially it's just a consequence of people liking to collect things. I think people just like it. They like to collect things. I like to collect things too. I like to collect like music, for example, and audiobooks. I'm going through like an audiobook phase, so I have like 10,000 audiobooks. No, not really. But anyways, people like to collect. So partially it's a consequence of that. Now, data visualization is using computer graphics to generate interesting pictures of data. I also like to think of it as the non-fiction version of computer graphics. So if I use the phrase computer graphics, you usually think of what? What do you usually think of when you hear the phrase computer graphics? Movies, exactly. Movies like the best movie of all time, Lord of the Rings, right? You think of Toy Story, Lord of the Rings, Star Wars. And you also think of games, right? Computer games. Well, data visualization that's all fiction, right? To take you away from reality. Data visualization is using computer graphics to bring you closer to reality, to depict reality, something that's actually happening, and not something that's like just not happening, like with no correspondence to the real world. The attendance register is somewhere. Did everybody sign it? It only took an hour. So what is data visualization good for? It is good for exploration. That's if you have a data set that you don't understand, right? You've just downloaded it, you don't understand it, you didn't collect it, and you just want to find out like what it is, if there are any patterns, any outliers, just to get a general overview. We can use visualization for analysis. This is what you'll start to do in your PhD. You have a hypothesis. You just start with a hypothesis. I believe this, and then you analyze data to confirm the hypothesis or refute the hypothesis. That's analysis. Then presentation. Everybody's very familiar with using data viz for presentations like pie charts and bar charts and line graphs and things like that. There are some other more subtle good things about data visualization. It's good for making things a lot faster. So you can see things like patterns and outliers and some characteristics of data much quicker than if you didn't use data visualization, right? If I gave you a spreadsheet and you know, of all numbers, and I said, please just tell me what the minimum value is, right? If there were 100,000 numbers there and you had to read them all to find out what the minimum was, then it would take you a long time. And you'd make an error too. But if you use data visualization, you can find the minimum in a second, right? Just a second with no errors. It's also good for increasing confidence, which is not something that's so obvious. So when you can see your data and make decisions on something you can see, then your confidence increases. Like you think, oh, what I'm doing is actually correct, or what I'm doing is incorrect. That's actually usually what happens. As soon as you start to generate pictures of your data, you find out that there's an error somewhere. That's actually usually what happens first. But then you fix the errors and move on, and now your confidence is increased that what you're doing is actually correct. So it's good for all those things. Okay, here is where the audience decides what's going to happen. So we have, these are the examples. These are all examples of different data visualization projects. Like they're not just bar charts, line charts, and the pie charts, the things that you're familiar with. They're more advanced, and they come from different disciplines. So I think there are 9 examples here. There's an example from physics, bioscience or marine biology, business, sports, healthcare, computational biology, engineering, motor simulation, and just a general flow visualization example. So we can't look at all 9 of those examples because it would take too long. So I'm actually going to ask the audience which example they would like to look at first. I guess what we can do is, just with a show of hands, perhaps, everybody can vote on which one. So raise your hand if you're interested in seeing the physics example. Okay, 1. The marine biology and bioscience, I'm going through in order. Whoops, I'm going through in order here. Animal, it's for animal tracking data. That one is like the marine biologists attach sensors to marine wildlife, release the marine wildlife into the ocean, and then bring them back and try to figure out what they did. In the meantime, any votes for that one? Actually, I should describe them first, and then we should do the vote. The business one is understanding call centers and their customers, right? So there is a company called QPC, and they develop database software that records every event in a call center, like when people call, what their phone number is, how long they spend in the IVR, like dialing those different menu options, how long they wait in the queues, which agents they talk to, and so on. And they collect that for years, and they want to understand what's happening. That's what this example is about. Sports video visualization. Anybody here watch rugby? I know lots of people here watch rugby. Well, some people at least. All the Welsh people. I guess Italian people too do watch it. Yeah, and French people and stuff like that. So I don't need to explain that, but you can visualize the video of rugby games, and that's what that example is. Then there's the healthcare data. So every time you visit the doctor, every time you visit the doctor, right, the data is recorded. Maybe you received some diagnosis, like a lot of people here are studying cancer, right? So a lot of people are afflicted with cancer in the UK. And this is an example of trying to visualize that healthcare data, right, in some sophisticated way. This strategy is about coupling it with the geography. So it's how do you couple this multidimensional data with geography. There's computational biology. So this is simulation data. This is biochemists or computational biologists studying the interaction of lipids and proteins on a simulation level. and they run the massive simulations, and they want to find out. We'll do a vote after I've done the
Okay,
descriptions.
okay.
Yeah.
Just
For future,
Besides, yeah.
future. Engineering, so anybody know what a cooling jacket is? That's the part of your motor that transfers heat away from the engine block, right? So your car doesn't overheat. Anybody ever have their car overheat before? Yeah, it's fun. It can like explode. And nobody had an engine seize. Like that's what happens. Your engine seizes, so it gets stuck because it overheats, and then the lubrication boils, and then the metal gets too hot and it fuses together. No, it's never happened to anybody. It's good times. So there's an example of visualizing flow through a cooling jacket. This is another one of motor simulation. It's a combustion example, visualizing the flow inside the combustion chamber of a motor vehicle. And then this is a general texture-based flow visualization example, just very general for any flow visualization or vector field visualization problems. Question? Did you have a... You like the last one? Okay, so we're going to take a vote now that we understand. Does anybody have any questions about the examples before we take a vote? The suspense is really high right now. I can feel it. It's really cool.
What is about the heat map and those things? In which part of
Heat maps?
Yeah, for the expression.
I don't think think heat maps are covered in these examples. So these examples are a little bit advanced.
Okay.
In a heat map is a good visual design, but like our job or my job, let's say, is to come up with new things and try to do new things. So heat maps aren't new. Mm-hmm. So I that's not my job. Okay. But the second half of the lecture is not about new stuff. It's about using Tableau.
Okay.
Right. So it's a hands-on exercise. Yeah. Okay. So raise your hands for physics. Three-ish, 3.5. Okay, so that's pretty good actually. That's kind of a lot. The marine biology example.
Just for curiosity in the end.
Yeah, we might have time for more than one example. Maybe two or three. Maybe we'll see. The business one, 2, call centers. The sports I'm surprised there aren't more. Yeah, only 2. Like everybody here watches rugby. Well, the guys do, I guess. Any of the females watch rugby?
Sometimes.
when you're drinking.
Yeah,
the healthcare example. Okay, that's a lot. 1, 2, 3, 4, 5, 6-ish. That's looking good. The computational biology. Oh, that's a popular one too. 1, 2, 3, 4, 5, 6, 7. Oh, that's the most popular one so far. That's surprising. I didn't expect that. Cooling jackets. 1, 2. Almost 3. Like 2.5. The combustion chamber example 1. Mm-hmm. And the texture-based flow is 1, 2, 3, 4, 5, 6-ish. That's popular too. Okay, so the computational biology is the clear winner for the first place. So we'll start with that one, and then we can have a vote between the healthcare and the texture-based flow viz, because that was the second ranking one. Okay, good. So I have to skip past the other examples for now. The computational biology example. So this is actually the simulation data is coming from a computational biologist in France, actually, in this case. who used to be at Oxford University. Oxford University happens to have a huge computational biology group of like at least 50 people in it, just all doing computational biology. It's a serious team, group of people over there. And they asked us if we could help them visualize their data. So that we are actually, this is work in progress. These are our initial attempts to visualize the data. It's still ongoing work, actually. And they are trying to understand the interaction between lipids and proteins. And I can't tell you the details about why they want to understand the interaction between lipids and proteins. I don't know all the consequences of this, but I believe them when they say it's really important and they really want to understand that. Right. So just in keeping with our beautiful analogy in the beginning, remember this pattern of knowledge evolution with the real world and the digital world? That's what these notes are about. If you wanted to study the interaction between lipids and proteins in the real world, people do that, right? They use tools, they run experiments, and they use nuclear magnetic resonance spectroscopy to study the real interaction. But those machines are very expensive, right? I don't even know, maybe 50,000, 100,000 pounds or something like that. Because the real world solution is so expensive and so difficult, they use a digital solution to study the interaction, which is developing simulation software. And of course that results in huge simulation data sets, right? Really huge, so that they all struggle with these very large data sets. So it happens to fit that model of knowledge evolution exactly. It's a perfect example. Okay, so let's look at a demo of that, if we can, hopefully. This is an interactive demo of some visualization software that we use to study this problem. Right. Now what we're seeing now are all the paths that are traced out by the lipids as they move over time. So the lipids and the proteins are moving over time, and they trace out paths. And there are hundreds of thousands of these paths. And when they collide, right, that's the interaction, right? When they get within a certain distance of each other, it's considered an interaction. So in some ways, the question boils down to how do you visualize or depict hundreds of thousands of paths or trajectories? And that's what we're seeing. Those are some individual lipid trajectories, right? And they've been color mapped to different properties. In this case, they're color mapped to total path length, right? And that is the motion of some individual lipid trajectories, right? So that's the user actually adjusting the time step to see the evolution of the paths over time, focusing on just a few of them. That's an overview of all the paths over all the time steps, right? So when you have that overview, the question is, well, then how do you filter the paths based on different kinds of properties so you can focus on certain subsets, right? If you're given a huge data set of hundreds of thousands or millions of data points, how do you then interact with it so you can select subsets of interest and filter them based on the different properties? And that's what this is demonstrating. Different ways of selecting subsets of the paths. So this one is just selecting, for example, the curvature and saying, show me all the areas where the paths have the highest curvature. Right? So the user can interactively adjust a curvature metric. And this is based on total path curvature. This is something we call normalized path curvature, which just means it's averaged. It's been averaged, right, over the whole data set. So these are the areas with the highest normalized curvature, right? This is the user changing the curvature interactively, and then watching which subsets have the highest curvature, or the curvature that fits in that.
Sorry.
Yep.
Is this data pre-rendered by any chance?
Pre-simulated, you mean?
Yeah, sorry.
Yes.
It is, because it's so quick. I was like, how does it calculate that kind
No,
of
no, no.
that's pretty
The simulation happens first,
All right.
and the visualization happens second.
Right.
Yes, so the simulation already happened.
So it means that you're already working with a database that has pre-calculated that particular, for example, lipid has that kind of curvature around that time and so on.
Exactly.
Right.
Yes, yes. And there are like endless sources of that simulation data.
That's still pretty impressive.
Yeah.
That's pretty nice.
Yep. This is one of the rare examples also that you can actually download and use if you want. Right? There's a PhD student, Nai Al-Habi, actually working on this, and he has released the software. So I can tell you more about that after, if you're interested. And so this is basically, all of these controls are filtering mechanisms, basically. Filtering by things like path length, curvature, and other different kinds of properties, maybe time. Now he is using some interaction to rotate the data set and show it like from the side. Right, the paths actually have a depth to them. They're three-dimensional trajectories. So he's exploring the three-dimensional space of the trajectories, and we can project them onto a 2D plane to simplify them, or we can visualize them in 3D space. So that's what he's doing here. He's showing what happens to a path in 3D when you project it onto a 2D plane. And you can use depth as a filter. You can say, I want to see all the trajectories that pass through a certain depth, right? Not all of the trajectories, but see what happens to them as their depth changes. It's a very simple idea, actually, but it's one of my favorites. It's really interesting to see the depth of the trajectories and see how, because they're modeling a membrane, which is a thin structure. And that's some overview of the membrane. Maybe I should try to turn off these lights. Anybody have an idea about where the switches for those lights are?
It may be on the console.
This one over here, do you think? That would be a logical guess.
Sorry, can I ask you a question?
Mm-hmm. Yep, definitely.
Because, I don't know, if I want to see a trajectory of a cell in a scaffold, because I want to build a 3D model,
Yep.
I didn't understand which is the input I have to give, for example, to this software
Yep.
to design the trajectory. Because maybe it is interesting. I
Yep.
can stay in myself and, I don't know, follow the fluorophore, so the cell
Yep. Yep.
in the scaffold.
Yep.
But what I have
How do you
to...
how do you filter based on space? It sounds like that's what your question is, like filtering based on space, or decide where in space you want to see.
Uh-huh.
Is that what your question is?
They use spectroscopy to give you this data.
We used a simulation. Well, I didn't use it, but there are simulation software, molecular dynamics simulation software. This one's called VMD, I believe, or
okay.
it's connected to a tool called VMD.
Okay. So they give a protein and those lipids, and then simulate the trajectory.
Their motion. Yep. Yep.
Oh.
That's right. That's right.
So I cannot extract those data from a real experiment. Because I'm curious on, okay, I can use the software maybe,
Yeah.
but I don't know what I have to give it in input.
Oh, I see, I see. In this case, you need, in this particular example, you need molecular dynamics simulation data.
Oh,
And it comes from a specific simulation piece of
Okay.
software.
okay.
Yeah.
So
That's
maybe
right.
I have to start from the software.
You
first.
wouldn't be able, I don't think you'd be able to use this software for your special purpose.
Yeah, I was asking
Yeah,
for
that's the question, yeah.
that. Yeah.
Yeah, this is for a very specific purpose.
Protein and okay.
Protein
case.
lipid interaction, that's right.
Okay.
Yeah.
Just
Anybody find the light switches yet?
Behind the curtain over there.
Behind the curtain?
Have it. You just won't be able to see it from where you stand.
This thing?
Switch that does nothing.
Why would a switch do something? Nothing over here, right?
Unless it's outside the door.
That would be cool. It's outside the door. I see some buttons. Okay, those are just. Those are just power buttons.
Behind the monitor. Like on this side. Yeah.
Like here, you mean?
Yeah, yeah.
Yeah, I looked there already. I couldn't find anything. Usually they're they're either here or by the doors. That's usually where the light switches are. Oh, well, okay. Well, if anybody discovers the light switches or thinks they have an idea, we need an app that tells us where the light switches are. Let me know at any time. Yeah, if you happen to discover where you think the light switches are. Yep. Any other questions about that particular example? Yeah, did you find them? I looked there, yeah. Maybe they're hiding in the cabinets. That would be cool. No, it's just a PC. There's nothing else. Okay, good.
Check those two rooms. Their room.
Inside the rooms here.
It's the switch room. Switch room.
I like the way you're thinking outside the box. I mean, that's because I wouldn't have thought of going in there and checking. Cleaners cupboard. Oh, look, there's a cat door. It's pretty cool. It's locked. Okay, good. Any other questions about that example? By the way, you can find that example on YouTube. So if you want to watch it more, you can see it on YouTube.
When you have a solution like that to a problem that groups come to you with,
Yep.
like when you're building an application like that, what are you building it in?
We generally use, not always, but generally we use C++, a GUI library called Qt or Qt, and a graphics library called OpenGL. So the combination of those three. Usually, not always, but.
Is it simple to exploit speed of it? Or is it just, is it simple to exploit the speed of it? Or is it simply because you're familiar with it?
OpenGL and Qt is so
Yeah, there are a number of reasons. So they're free. They're all free. They're all very mature. So they're used all around the world. They're well documented, as he mentioned. They're very good with performance. So if you want to get the fastest performance. And it happens to be a very marketable set of skills. Like if you're good at these tools, you will never have a problem finding a job for the rest of your life, and there will be companies competing for your expertise, actually. We had a student, a PhD student that graduated. He got a 10,000 pound raise before he started because 2 companies were competing for him. So it's a good set of skills to have. And I also will never forget the day a student was making fun of me, a fresh PhD graduate for having a higher salary than, I have a higher salary than you. It's like, I can't believe you're telling me this. Anyways. Okay, so we can do one more example, I guess, before we do the hands-on part of the course. And the 2 popular ones were the healthcare and the texture-based flow-viz. So we'll take another vote between those 2. Who would like to see the healthcare? That's getting fewer votes the second time. That's interesting. And the texture-based flow-viz? Okay, I'm surprised. Okay, that's fine. And by the way, all of these examples are on YouTube, so if you're interested in seeing any of the other examples, and a lot of them have voiceovers, like somebody sitting there with a microphone and explaining what's happening, and so on. And so you can find all the examples with explanations on the DataViz YouTube channel if you're curious. Okay, so the texture-based flow-viz example. Does everybody know what vector field data is? Anybody want to explain to the rest of us what vector field data is? Anybody?
It's where at every point in space you've got a direction and a magnitude. You've got two numbers associated in space.
Exactly,
like
exactly.
Simulating a liquid flow. You've got the speed of the flow and which direction it's going.
That's exactly right. Did everybody hear that? So most data that you sort of are familiar with is called scalar data, so it's just one number. It represents a magnitude. This is vector field data, which means it has a magnitude and a direction. Right? If I rob a bank and then I'm trying to get away in my car and the police see me, like a police car is sitting there like having donuts and they see me drive away, or somebody sees me drive away and they're trying to tell their colleagues like, oh, I just saw the robber. They would ask two questions, right? Like, how fast was he driving? Like maybe 200 miles an hour, obviously. But that's not very helpful, right? If I just say, oh yeah, he was speeding on the M4 at 200 miles per hour, that's not very helpful, right? There's something missing from that, right? What would you ask in addition to how fast I was going? Which direction I was going in. You'd have to say like west, east, north, south for that information to be more useful. So that's a speed, a magnitude, and a direction. That's vector field data. So this is about a visualization technique to see fluid flow, which is also has a speed and a magnitude, so a direction. All the examples in this case happen to be, this is a special algorithm for surfaces. And what it does is it puts a texture, a noisy texture on the surface, and then the texture is smeared in the direction of the fluid flow. So we can see the fluid flow behavior on the surface of all these geometries. And there are a number of different geometries. Anybody want to hazard a guess what that thing on the left is? This will be fun for the medical students, the medicine. This is exciting. This is going to be exciting for some of you, I think. It's a CFD simulation of an aneurysm. Yeah, all your medical. So the blood flow is coming in the bottom, so to speak. and then it's getting stuck in the pocket, and then it's trying to flow out the two arteries. So that bulge is an unhealthy aneurysm, right? It's preventing the circulation of blood flow, proper circulation. And on the right, anybody know what's on the right?
Engine casing.
That's our cooling jacket, our friend the cooling jacket. So let's see that in action. I like this thing because I never know what the audience is going to guess. I like that fun part. So this is what that example looks like. This is actually from my PhD, so this is what I was working on during my PhD. Right, and this is just visualizing the flow on the surfaces. And they're all from CFD simulations, right? That's what the fluid flow at the surface. These are intake ports from an engine simulation, and this is the combustion chamber. So you can see how the fluid moves at the surface of that geometry, right? You can see which direction it's moving in. You can get an idea of how fast it's moving, and it covers the whole surface. It doesn't leave any holes or missing areas. It gets everything, right? You can't miss any spots with this technique, and that's what makes it interesting. Is you can't miss any piece of the surface because it covers the whole surface, right? These are just some aspects of the technique that we had to make sure are working properly, right? So that we can see edges clearly, right? That's a demonstration, just saying, look, this visualization technique detects edges in the image and then handles them so we can see. So if we watch the edges down here, they pop out at a certain point. That's what it looks like when we apply the technique to the cooling jacket, which is very complicated, right? This is a very, very complicated geometry, really, really complicated. And the yellow are areas of slow moving flow, by the way, in this. All the color maps that we see are vector field magnitude. And if your flow is moving too slow through the cooling jacket, it causes problems, right? Because it's not transporting the heat away from the engine block, and it can start to boil. It's also called cavitation. This is the aneurysm example. So looking at the flow at the surface of the aneurysm, so you can see how it enters the cavity, and then it starts to recirculate around the cavity before moving out again, exiting. So I like that example because really CFD simulation is used for everything. Like it's everywhere now. This is actually 1/2 of an engine cycle. So some of you might have noticed that your pistons in your car and your motor move up and down, right, at about 1,000 rotations per minute. And that's 1/2 of a valve cycle, right? What happens, what the flow looks like at the surface of the combustion chamber after 1/2 of a valve cycle.
Sorry.
Mm-hmm.
But this only gives information about how the flow is next to the edge, not what's actually inside.
That's correct. That's correct. So we have other examples that show the inside of what's happening. So we can take a slice through the geometry. That's a good question, by the way. We can take a slice through the geometry and then show what's happening. There are lots of different possibilities. Well, now that you asked, I can't resist, and I'll show the other related examples that cover the different spatial aspects, like two-dimensional slices and surfaces and some 3D vector field visualization techniques. So this is closely related. That's the same technique being applied to a slice. And those are so-called streamlets, which are short streamlines seated on a slice through the combustion chamber. This is visualizing so-called tumble motion. So this is the combustion chamber again, that piston valve cycle, but with a slice taken through it. That's using dye injection. So it's the same technique, but the input texture is different. So it's simulating the injection of dye rather than noise. So here it is on the boundary again, similar to what we already saw. The user is just modifying some of the algorithm parameters and then watching the effects. There are patterns there that the engineers are looking for that I haven't gone into detail explaining what those patterns are, but you can notice some features of the flow, like a saddle point there and a vortex there, for example. Right, here's a vortex, and that's a so-called saddle point in the flow. Anybody studying flow or vector fields will know what those are. But a vortex is pretty obvious, right? It's an area of swirling flow. And that's using streamlines in 3D to visualize the volumetric aspect of the flow. And this is kind of some more 3D flow visualization. These are so-called seeding planes. So we seed streamlines from these little planes that are positioned inside the volume. And here we're using a combination of techniques, isosurfaces, streamlines, and texture-based flow visualization. And here's some combinations of techniques being used again. So these things could be applied to something like blood flow. Question?
Sorry.
Yep.
So I think that's another question.
Yep.
What program do you use for doing the simulation?
This is a difference. See that company, AVL? They're the ones that own the simulation software in that case. So it's not...
So you just did the visualization, not the real computation of the flow.
That's correct. That's correct. So there's, again, it's this situation where there's simulation software.
Because normally in the flow, the software that makes the computation for the flow gives you straightforward visualization.
Yes, how do you
When
know?
it's limited, then maybe
Yeah.
and just a visualization software will give you other features.
How do you know that? That's very unusual knowledge.
I already worked with that. Already
Yeah,
did
you worked.
simulation.
You worked for a company that did see it.
No. I just say that I already did flow simulation.
Okay, where did you do flow simulation? It's not very common.
My master.
Okay,
My master.
which university was that?
I'm from Portugal.
Okay, somewhere in Lisbon or something like that. Okay,
Technical.
good. Yes, so you must have found that kind of interesting then. Yes, so AVL is one of the many companies. There are many companies, as you know.
The software is not free.
Correct. The software is not free. Yes. And that was actually my PhD project. So this company, like, said, we will sponsor your PhD, and we'll give you a salary, as long as all of your visualization software is embedded directly into our commercial products. So it's all embedded in their commercial products, and now they have the visualization software and they can sell it. Yeah. So it's a very unusual situation, actually. Yeah.
I use console multiphysics.
Okay. I'm not familiar with all the the flow simulation. I know that here TechPlot is one of the big simulation packages. And which one?
Console.
Yeah.
COMSOL?
Yeah.
Okay, I'm not familiar with that one.
As the name says, multi-physics, that you combine heat, flow.
Mm-hmm.
Yeah,
Mm-hmm.
it does all the electrical flow stuff, the heat stuff,
Mhm.
stress, any kind of simulation you pretty much think of.
That's really great. That's really great.
It's just very user-friendly.
Yep. Yep.
Could I ask another question? That's okay.
Yes, of
So the thing
course.
is that so far you have shown an excellent method of visualizing the data, but is there a way to extract some sort of quantitative answers out of it? For example, okay, you can say that the streamline is such, for example. Can you
Yep.
then make a mathematical model of that streamline and say, you know what, maybe this can be optimized, and you can maybe make it, if you change, for example, the geometry of the vessel in such a fashion, then you optimize the flow by such and such.
Yep, that is the ultimate goal. That's like the holy grail, so to speak.
So it's tricky.
I'm gonna, if I lean too much against this table, I'll fall over. So, what happens in reality, in those examples, what I didn't mention is there's misbehaving flow.
Yeah.
So there are places where the flow is not pointing in the right direction. And so the engineers see that, they say, oh, the flow is not doing what it's supposed to do. And then they have to make a judgment, how can we modify the geometry to see if we can improve that situation?
And how do you know that you're not limited by the mesh, for example? Maybe you made a bad mesh and then it's just numerical nonsense rather than physical nonsense. And
That's
how-
right, so they
how
have
do you-
to do some remeshing, they have to modify the geometry, go back to the beginning,
Okay.
modify the surface geometry, then go build the volumetric mesh, then rerun the simulation, and then see the results again. So it's a laborious process.
In the meantime, your computer can be the problem because it's too slow.
Oh, dear.
Yes.
You increase
Yep.
the mesh because you want to see more detail. Your computer not to the simulation.
Yep. I'm surprised. I have not had anybody that's been that close to this topic before in the class. You're making me nervous. No, because this class is so enthusiastic, I can keep, I'm not going to keep showing examples, but I'm at least going to show you. So this is a topic we've been working on since 2001. So we have a lot of work in this topic. So I'm just going to show you where you can see it. Right? We could do a course, a full module just on this topic, on the topic of flow visualization. And those things do exist in some parts of the world. So if I go to my web page, for example, and then click on teaching, we have a data visualization module. And then we can click on the DataViz YouTube channel. And you can see all of the things that we've been working on with flow, and lots of different examples. So if I click on playlists, and then, well, there's the data visualization lectures, but for FlowViz specifically, there's a list of research videos. And a lot of them are flow visualization, but all the examples we were going to go over today are there. So there's a recent one, a stream ribbon seeding strategy. There's the molecular dynamics. That's one we just sort of looked at, except it's supplementary material. There's a resampling tool for CFD simulation data. There's flow past marine turbines. There's the foam viz. This is visualization of input parameters for stream and path line seeding. So you can keep going. There are like 40 videos. They are all in like at least 20 of them are flow viz, different aspects of flow viz. So it's a really big topic. So I couldn't resist mentioning that because of your experience and the questions. Any other questions about those two examples? I would suggest that we take a little break and then we do the practical part next. So the practical part is using the Tableau software, so finding it on the PC is going to be like step 1. The Tableau public data software. You don't have to follow along, you can just watch if you want to. And then we're gonna choose a special data set to look at. If you go to my webpage and you add the word data, you can find the data set we're going to demonstrate looking at. Everybody here? Well, anybody that wants to actually follow along. And then we click on car. And it's in the car. It's in the car directory in the UK, since we're in the UK. The actual data set is called Accidents 2015. Yep. So did you find this?
Yeah.
This one?
No, fine.
You found that? Okay, then you add the word data on the URL. DATA. And then car. Click on car. And then, well, you have no other choice. UK. And then accidents 2015. That's the actual data set. You can download the other files too, but those are metadata. Those are not the actual data we're going to look at. Any questions about that before we take a little break? Okay, let's take a let's take a 5-minute break, I guess. Yeah.